Iapetus, Saturn's mysterious moon, is slowly drifting into the giant planet's shimmering rings, moving at a speed of about 3.2 kilometers per second. And according to research from the Cassini spacecraft, this process may take millions of years to complete. Yet the effects it is already creating are producing changes in the ring system that are almost beyond imagination. Dust trails, fragments, and strange materials are being expelled, forcing scientists to confront urgent questions. Could Iapetus eventually become part of Saturn's rings? Or will this collision open a new era in our understanding of the universe? The mysteries surrounding Iapetus not only capture scientific attention, but also challenge our current knowledge of how the cosmos works. And the strange, paradoxical journey it is undertaking may hold the key to unlocking some of Saturn's deepest secrets. A silent yet powerful process has been unfolding for billions of years. A collision that produces no explosion, no violent shattering, but is persistent enough to reshape the ultimate fate of this moon. Its slowness and endurance are what make it so formidable. A mechanism unlike any type of impact humans usually imagine. And to understand it, we must step away from Iapetus's surface and look outward, toward a much smaller moon playing the central role, Phoebe. Phoebe orbits Saturn in a retrograde direction, a signature trait of a captured object, possibly originating from far beyond, perhaps from a region as distant as the Kuiper Belt. Its composition is rich in carbon, dark, cold, and fragile. For billions of years, impacts from micrometeorites have blasted countless dust particles from its surface. And over time, those particles did not disperse. Instead, they formed an enormous structure, the Phoebe Ring, the largest dust ring around Saturn, stretching from about 6 million kilometers to more than 12 million kilometers. Despite its extremely low density, its sheer size makes the total amount of dust substantial enough to influence any body passing through it. Iapetus orbits right inside the region swept by the Phoebe Ring. But the dust does not simply fall onto Iapetus by itself. It needs an invisible push, and that push is solar radiation. Photons streaming through the dust ring, colliding with each grain and producing a slow drag known as the Poynting-Robertson effect. As this force continuously acts on the dust, it loses orbital energy and slowly spirals inward. Meanwhile, Iapetus orbits Saturn in the prograde direction, while dust from Phoebe moves retrograde, creating a very high relative velocity between them. us. Every speck of dust, tiny and light as soot, strikes the leading hemisphere of Iapetus with enough energy to disrupt its microstructure and adhere to the surface. The effect is similar to a car speeding through the night. The windshield collects every insect in its path. On a cosmic scale, Iapetus is that windshield. A moon forced to plow through Phoebe's retrograde dust stream on every long orbit. The strongest evidence for this mechanism was recorded by the Cassini spacecraft during its close flyby of Iapetus in 2007. It detected a dark coating only a few centimeters to 1 meter thick, far too thin to be produced by any internal geological activity. Impact craters exposing bright, pristine ice beneath the surface made it clear the dark layer is not native bedrock, but a coating. A shell accumulated from the outside, particle by particle, molecule by molecule, over billions of years. Remarkably, orbital models from 2023-2024 precisely simulated Iapetus's current path through the Phoebe ring. And the results showed that its leading hemisphere lies exactly in the region of highest dust concentration. Meaning, Iapetus's orientation and rotation make it the perfect target for this incoming stream. But this collusion mechanism does not end with dust simply coating the surface. As the dark layer grows, it absorbs more sunlight, causing the darkened regions to heat up and trigger sublimation of the ice beneath. If this process continues for billions more years, models from 2024 predict that an average of 100 meters of surface ice could disappear every billion years. A tiny number on human scales, yet monumental when compared to the age of the solar system. This leads to a profound philosophical consequence. Cosmic collisions are not always explosive events. Sometimes the most transformative forces come from the gentlest touches. The quiet grains of dust without sound or light, which, when given time, become powerful enough to reshape a world. So, could Iapetus eventually disappear? Over time, its surface ice may erode, its structure may gradually weaken. And in the distant future, material stripped from Iapetus may become part of Saturn's ring system. As we move closer to Iapetus, we step into a paradox, a moon split in half by two opposing colors so extreme they appear as though they belong to entirely different worlds. The dark region, Cassini Regio, named after Giovanni Cassini, covers nearly 40% of the surface. With an albedo of only 0.03 to 0.05, equivalent to a tar-coated landscape. Every photon of sunlight that falls onto it seems to vanish without return. In contrast, the bright hemisphere reflects light with an albedo of 0.5 to 0.6. Nearly as bright as Enceladus, one of the most reflective bodies in the solar system. The two halves of this moon differ so drastically that if you place them side by side without context, you might easily believe they came from two separate worlds. On most moons, materials mix. Heat causes sublimation. Ice migrates, and solar wind erodes. Everything blurs the surface into gradual transitions of texture and color. But Iapetus breaks this rule. Its boundary between dark and light shows no transition from gray to shadow. Or from white to pale. Instead, it is a sudden, abrupt leap from bright ice to pitch black dust. Spectral data from the Cassini spacecraft, reanalyzed in 2023, revealed that the dark region contains high concentrations of carbon. Complex organic compounds, such as PAHs, and spectral signatures matching dust from the Phoebe ring, the massive dust structure surrounding Saturn and sourced from the retrograde moon Phoebe. This confirms that the dark coating is not native to Iapetus, it is an external layer. Yet this is only the surface of the mystery. The layer is astonishingly thin, measuring only a few centimeters to about 1 meter. The interplay of heat, ice, and time creates a cycle so slow it cannot be observed within a human lifespan. Because Iapetus rotates once every 79.3 days, one side faces the sun for extended periods. And it is precisely this Cassini region that absorbs the most solar heat. As the dark surface warms, the ice beneath begins to sublimate, releasing thin vapor from a world nearly motionless in every other sense. As the ice disappears, the dark dust becomes even more exposed, increasing absorption and driving the region into a self-amplifying thermal loop. This feedback cycle is what allows Cassini Regio to remain a deep, persistent shadow, sustaining itself over billions of years. Meanwhile, the sublimated vapor does not vanish. It migrates to the colder, bright hemisphere. There, the vapor freezes and accumulates as fresh layers of white ice, enhancing its powerful reflectivity. This implies a profound truth. The brilliant side of Iapetus was not gifted at birth. It was built slowly, molecule by molecule, over billions of years as drifting vapor settled into the cold. Physically, this means the bright hemisphere continues to brighten with time, while the dark hemisphere sinks deeper into blackness. Thermal model simulations published in 2022 showed that Iapetus possesses the strongest feedback cycle ever recorded on any body in the solar system. Here, light and darkness are not mere surface states. They are the results of an ancient battle between energy and matter, between heat and ice, between accumulation and erosion. What is astonishing is that this entire process unfolds in near silence. No violent collisions, no shattering ice cliffs, no volcanic eruptions. Only dust, sunlight, and time. Three subtle forces which, when woven together, create one of the most spectacular phenomena in any planetary system. However, this thermal feedback loop is only part of Iapetus's transformation. Because lying directly at the intersection of this stark light-dark divide is a geological structure science has yet to fully explain. An equatorial mountain range rising nearly 20 kilometers high, positioned absurdly precisely along the equator, stretching more than 1,600 kilometers. Between darkness and light, between the invisible cycles of erosion that span billions of years. Iapetus carries a signature so unusual that even NASA describes it as unlike anything we've ever seen in the solar system. A colossal equatorial mountain range stretching across nearly the entire circumference of the Moon. Standing upright like an ancient wall, dividing a world already split in two. No moon of Jupiter, no satellite of Uranus or Neptune. Not even the distant icy bodies of the outer solar system possess anything remotely comparable. Only Iapetus holds this giant spine, a wonder Cassini observed up close in 2007. Instantly recognizing it as a story that did not belong to any familiar orbit or ordinary geological process. The ridge spans 1,600 kilometers, is roughly 200 kilometers wide, and rises in some places to nearly 20 kilometers, taller than Everest in absolute height. What confounds scientists even more is its absurdly perfect placement. The ridge sits exactly along the equator, not even a single degree off. Precision nature rarely produces unless shaped by extraordinary events dating back to the earliest days of the solar system. There is no surface tectonics, no internal compression, no magma pushing upward from below. So what could raise a frozen wall thousands of kilometers long? Scientists propose two major hypotheses, and though they differ in mechanism, both lead to the same conclusion. The ridge is one of the oldest surviving features of Iapetus, possibly dating back more than 4 billion years. According to the traditional hypothesis, early Iapetus may have rotated far faster than it does today. Perhaps with a 16-hour day rather than the current 79.3 days. With such rapid rotation, centrifugal force would have been strongest at the equator, pushing outward on the moon's soft, mostly icy crust. If Iapetus' surface was still partially molten or weak at the time, its materials would not resist the outward pull. The moon would bulge like a fast-spinning sphere, forming a dense equatorial band. Later, as tidal interactions with Saturn slowed its rotation, the surface cooled and froze into the stretched shape, leaving behind a solidified ridge of ice. This model explains the ridge's great length, the walnut-shaped outline of Iapetus, and the similarity between ridge material and surrounding terrain. But how does a soft early structure preserve a height of 20 kilometers once frozen? And why would the bulge manifest as a sharply defined wall, rather than a broad equatorial swell, like those seen on fast rotating planets? These questions make the second hypothesis more compelling. In this scenario, a small moon of Iapetus, or another icy body, may have been torn apart by tidal forces, forming a miniature ring system around the moon, similar to Saturn's but vastly smaller. If this ring lay within Iapetus's Roche limit, its fragments could never reassemble into a new moon. Over time, orbital drag and interactions with the icy surface would cause the ring to collapse inward. Every fragment would fall in only one possible place, the equator. Modeling from 2024 shows that the height, width, and sharpness of the ridge align almost perfectly with the ring collapse scenario, a process that may have taken tens of millions of years. If this hypothesis is correct, then Iapetus once carried a ring of its own, and the equatorial ridge is not merely a physical remnant, it is historical evidence. It preserves traces of ancient, rapid rotation, the aftermath of a massive collision, the imprint of orbital instability, and possibly even the ghost of a moon that no longer exists. with no tectonic activity to erase it, no rain or wind to erode it. The ridge has survived nearly unchanged for billions of years. It stands there still, not only dividing the moon's surface, but dividing its history. Before and after Iapetus settled into the cold, still form we see today. Under Iapetus's conditions, ice at extremely low temperatures becomes incredibly strong, almost rock-like, and at around -143 degrees Celsius. Icy material can bear long-term stress without deforming. And without meaningful internal heat or periodic warming, the structure has preserved its shape for eons. The ridge endures because Iapetus is a world of absolute cold and absolute silence. Two perfect conditions for time to turn everything into stone. The equatorial ridge is not only Iapetus's greatest mystery, it is the key to understanding the moon's entire geological and orbital evolution. But the story does not end here, because this colossal wonder is also caught in the same slow cosmic erosion that is steadily reshaping the entire moon. At the heart of this thermal feedback loop lies a simple yet profoundly consequential fact. Iapetus has a day that lasts 79.3 Earth days. This forces every point on its surface to face sunlight for an unusually long stretch of time. There is no rapid day-night cycle like on Earth, no mechanism for quick cooling, no winds or atmosphere to redistribute heat. So once any region absorbs sunlight, it retains that heat long enough for irreversible changes to unfold. At Cassini Regio, the dark hemisphere, the extremely low albedo of 0.03 to 0.05 means sunlight is almost entirely swallowed. Though the total heat gained is still modest by Earth's standards, the surface remains tens of degrees below zero. But because water ice is the primary material composing Iapetus, even a small temperature increase is enough to trigger sublimation. Remarkably, the carbon-rich dust coating the dark region is only a few centimeters to at most 1 meter thick, according to Cassini's 2007 data. The ice beneath this dusty veneer is easily exposed to sunlight. As the ice sublimates, more dust is left behind, the dark layer grows thicker, and that means it absorbs even more heat. A 2022 thermal model concluded that Iapetus has the strongest thermal feedback loop ever recorded in the solar system. No planet, moon, or asteroid exhibits a cycle as stable and long-lasting. Under Iapetus's low gravity and extremely thin surface pressure, water vapor travels easily across the terrain like a ghostly drifting gas. And when it reaches the colder region, the bright hemisphere, it recondenses into fresh ice. This creates a phenomenon not observed on any other moon. Iapetus is actively transferring ice from its dark side to its bright side. If we imagine Iapetus as a living sphere, we can see it slowly shifting material from hot to cold, like a world breathing in slow motion. The recrystallization of ice on the bright hemisphere not only preserves its brightness, but steadily boosts its reflectivity over time. With an albedo of 0.5 to 0.6. The bright hemisphere functions like a massive ice mirror, bouncing away most of the sunlight and keeping the surface so cold that sublimation almost never occurs there. Thus, while the dark hemisphere gradually loses ice, the bright hemisphere is continuously replenished. A natural polarity maintained by the fundamental physics of ice, light, and vapor. Even more astonishing is that this feedback loop not only shapes color and reflectivity, it directly alters Iapetus's terrain. As ice sublimates, the surface becomes more porous and weaker, easier for dust to settle on, and more vulnerable to deformation from even small meteoroid impacts. The bright hemisphere behaves in the opposite way, more rigid, more stable, becoming a cold reservoir that stores the moon's redistributed ice. Philosophically, this reveals that polarization is not just a surface effect, it becomes a transformative force that reshapes the material structure beneath. The feedback loop is rewriting the face of Iapetus. Not with magma, not with quakes, but with light, shadow, and time itself. Through the Voyager and Cassini missions, a slow and unsettling truth emerged. This is not a typical moon of Saturn. But an object that defies every familiar logic of how icy bodies form and evolve. First, consider the density of Iapetus. only about 1.2 grams per cubic centimeter, significantly lower than Titan, Rhea, or Dion. This value reveals that roughly 75% of Iapetus is water ice, with the rest composed of light rocky material. There is no evidence that internal heating ever melted or differentiated its layers, meaning Iapetus has remained nearly unchanged since the moment it formed more than 4 billion years ago. Its shape deepens the mystery even further. When spacecraft captured global images of Iapetus, it appeared like a giant walnut, bulging dramatically at the equator. Such a figure can only form if, in the distant past, Iapetus once spun at incredible speed. Dynamic models suggest it may have rotated once every 16 hours, before tidal forces from Saturn slowed it to its present 79.3-day period. While Iapetus was still warm enough to be slightly malleable, its rapid spin would have caused the equator to swell outward once the surface cooled. That shape froze permanently into place. This is evidence that Iapetus underwent a formation history entirely unlike the other major moons of its era. But while its shape may be strange, its surface is even stranger. The density of impact craters, ranging from hundreds of kilometers across to innumerable tiny pits, reveals that Iapetus's terrain is profoundly ancient. Some regions may be 4 to 4.3 billion years old, nearly matching the age of the solar system itself. This is a world locked in stillness, one that has experienced virtually no geological activity for billions of years. No cryovolcanoes, no resurfacing, no internal flows. And then there is its orbit, at 3.56 million kilometers from Saturn, nearly 3 times farther out than Titan. Iapetus sits beyond the strong influence of Saturn's magnetosphere and particle belts. This isolation makes it feel detached from the dynamic system that shapes the other moons, like a solitary fragment drifting on its own. Its orbital inclination, a steep 15 degrees relative to Saturn's equatorial plane, reinforces that idea. According to a 2023 analysis by JPL, this unusual tilt may signal that Iapetus was captured during the early solar system. This implies Iapetus may have formed elsewhere, perhaps in a region where small icy bodies were being scattered by intense gravitational interactions. Then, during the chaotic era of planetary migration, the period referenced by the NICE model. Iapetus was swept into Saturn's orbit and gradually settled into position. A world composed of 75% ice, without a clearly layered core, shaped like a spun-out object frozen mid-motion, carrying a surface almost as old as the solar system itself, and orbiting at a tilt so severe it seems as if it never truly belonged to Saturn. All of it forms a paradox. Iapetus behaves like a primordial ancient moon, yet it bears scars of dynamic forces from elsewhere. And from this long-standing strangeness, a phenomenon unlike anything else in the solar system emerged. The most extreme bright deck dichotomy known. It is not a temporary shift, as Giovanni Cassini once believed, but a deep, long-term consequence of its structure, orbit, and interaction with a surrounding sea of dust. The gravitational interaction between Iapetus and Saturn's ring system is not merely an intriguing astronomical phenomenon. It is a vivid demonstration of the universe's restless, ever-shifting nature. With its unusual orbit and steep inclination, Iapetus is undergoing a collision that moves slowly, almost imperceptibly, yet progresses in a direction that cannot be reversed as it grazes the outer edge of the rings. This gradual absorption of material and the reshaping of the ring's structure stand as living evidence that even the oldest satellites are never exempt from the dynamic laws governing their cosmic surroundings. The slow orbital drift unfolding over millions of years illustrates the fragility of structures that seem unchanging when viewed on human timescales. Although this process spans geological epochs, its final outcome is unmistakable. Iapetus, a solitary frozen world, is writing the last chapter of its cosmic story by merging into the grand architecture of its parent planet, becoming a testament to the laws of change and gravitational influence that shape every piece of matter in the deep expanse of space. This story reminds us that nothing in the universe remains still. Every world is moving toward an ending, shaped by gravity, time, and the slow fading of cosmic nature.
The slow orbital drift unfolding over millions of years illustrates the fragile structure of the shape.
Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.